Alright, hell yeah. So this is a material mechanics problem where things stretch out. So these springs kind of compress, and so when water's in the pipe it deplaces. So the original location of the pipe might be up here, you put water in it and it lowers because these springs are compressing. Now the other thing that happens is that these rods are made of steel, stainless steel, and this rod is made of stainless steel. And when you apply load to them, they will also stretch. It's kind of a fundamental concept of material mechanics. And so I solved this from iteration, and I just wanted to go through. I did not take into consideration the fact that these have weight, and that might influence. Yeah, I had to take a quick pause there just because. Yeah, so these have weight themselves, and their own weight is going to stretch them out. But you need an integral to do that, because if I'm just hanging this bar, if we just think of this bar as being hung from here, like this little slice right here, like how much tension is in it? You know what I mean? It's like none. But then up here, hell, there's going to be a lot of tension. It's going to be due to the weight of that rod. Now this setup isn't very large scale, so these weights aren't very big. Actually, pretty lightweight. I think this weighs 6 newtons, and this weighs 1 newton. So, yeah, this weighs about 1.5 pounds, and this weighs about a 1/4 pound. Yeah. Okay. So, but the why things lengthen is you have something pulling on them, but due to the hanging weight of this little section down here, there is no load on it due to its own weight. But up here, if we hang it, heck yeah, up here that little section has its weight. So we need an integral. And you do that. Sorry, everything's pretty small. I just wanted to kind of fly this video out. But the change in length equation is FL divided by EA. And so if I knew the force on something, then I know, and I know its length, and I know its material, and I know its cross-sectional area, I know the change in length of that. And so the force is going to vary as we go from this point up to there. And so we do that a lot in material mechanics. And just because it's vertical, I kind of forget. It's just like, hey, turn it horizontal, or just call this the x-axis. And then you're just going to solve for the normal force as a function of x. There's no normal force here, and there's a big normal force there. So this change in length is going to be the normal force as a function of x. And then you would need an integral. So if we're taking some little slice dx, I'm going to say the differential change in x is equal to, sure, the force on that's going to be, if I choose any dx slice, it's going to be at a distance x away. And so right here, heck yeah, this force is legit, and that force is the normal force at that point. The length of this is only dx, so that's where this is. This is going to be dx, and then the material property is a constant, and the cross-sectional area is a constant, doesn't change. If this does change, then you can have a prismatic bar. And so so this is the integral that we have. So we have d change in length is equal to this, and I kind of have it down here. That's where it is. And then once we just integrate dx becomes x, and we have the normal force as a function of the normal force as a function of moving along that axis. You know what I mean? Bigger up here, 0 here. Times x, and x is just going to be the length of it, and that's going to be EA. Oh yeah, I had to take another pause because I was just like, well, I just know from what happens is that you can just say, hey, like, yeah, there's no load here, there's hella load here, but what if we just halved? What if we just said the change in length is due to half the weight? You know what I mean? Let's say because the axial load up here is really large and the axial load right here is 0 and it's linear. Well, let's just take this same bar and just apply half the load, half the max load, which would be half the weight, and use that for our change in length. So then we just have change in length as half the weight times the length of this divided by EA, and that's what we get. Because we have the normal force as a function of x, like where's that integral that I did? So yeah, and then so to find the normal force at any little section, we need to find the force, you know what I mean? We have some sort of mass in this little slice. So that's going to be a volume slice, dx, dy, dz. And then we're going to have some sort of material density. So that's going to be gamma, which is force per area. Sorry, force per volume. Compared to rho. Rho is mass per volume. But we want weight per volume. And that's going to give us that small little force at that little section. The normal force is going to be adding these sections starting from here and moving our way up. So if I just have like 0 length or just a little bit of length, and this is the integration of 0 to a very short length, then this number approaches 0. You know what I mean? It's very small. I would basically just have, let's say my length was just dx, so I go integral 0 to dx. My force on that is just going to be the volume, and this is a circle, so we have pi r squared, or pi d squared divided by 4. That's going to be the area of that. The thickness of the slice would be dx, so that's area dx. There's our volume, and there's our weight per volume. Okay, so sweet. And so when we integrate from 0 to L, you know what I mean, 0 to x, 0, well, just, I guess for this is just giving us, we just want the normal force at any function of x. We don't want to know the normal force just at that point. We want an equation where we know the normal force at any value of x. That's what this is. If we threw in x is equal to L, hell yeah, that would just give us, that's the volume of it. We have this area of this circle times the height, and that would be the volume. So the area of that circle times the height is the volume times the weight density. But if you keep this as a function of x, then we know that our change in length is going to be this. So we're going to have weight density. I'm just going to put area, and then we have x, and that is this. So I'm going to have x squared, and then the a's cancel. So I'm going to have weight density x squared divided by EA. And that is going to give me the change in length due to the weight itself. And I'm sorry, I messed up. So this is our differential change in length. So I know the differential change in length is going to be, well, the change in length is going to be the integral of the differential change in length. And so so this value right here is going to be weight density AX, and then we have this dx. Sorry about that. And then so when we integrate, this is going to become x squared divided by 2, or 1/2 x squared. And so we're going to get 1/2 x squared. So, and that is going to be the same thing as taking the so let's show this by taking, we're going to take the area times the length times the weight divided by 2 as our force, and change in length is going to be force FL over EA. And then so this is going to be the force on that, so we're going to have AL gamma L to EA. A's are going to cancel, and we're going to left with gamma L squared divided by 2E. And so that's what we have here. This integral, which would be the change in length at any location from 0 to x, and you know, we would just throw in x. We would just evaluate x at the length 0 to L, and so that's what we get. We get gamma L squared, gamma x squared divided by 2e, 2e. Sorry, and then even here we already factored out our a term. Oh, because the a is right there. Sorry, I didn't include the a in the top, so that would factor out. So we've got gamma x squared divided by 2e. All right, hell yeah. So sorry about, I just wanted to kick this out. We'll see. And then I did an iterative video where, you know, I mean, I just didn't, I thought the equation was going to be, you know, you had to use a calculator to solve it. But no, so the general gist is that this thing is going to displace 82 millimeters. And so that's going to be the total displacement, which is going to be a sum of all the displacements in here. So the spring is going to compress, and then these steel bars are going to lengthen. So if we take into consideration all of that, then we can find and these change in lengths are due to the weight of the pipe. The weight of the water in the pipe is causing the force on these rods and on this rod and in these springs. And if we take also into consideration the weight of the pipe and the weight of the rods itself, it's not too difficult. So if I take right here this CD, I'm going to say the change in length of this is going to be the, so this is going to take half the load of the water in the pipe. So I'm going to say that's going to be, well, the change in length of this just in general is going to be due to the change in length of the weight of the water in this pipe, and then also the change in length of the weight of this rod itself, which is negligible. You wouldn't have to do that. There was no change. So if I take that into consideration, here is our answer anyway. And it didn't even get any closer to the answer in the back of the book, which was 20. You know, they just rounded to this. But this didn't even change to a 6. It didn't even change 1 Newton. So yes, the actual weight of these members don't change the displacement. But we're gonna account for them. And so, yeah, so the weight of the water in the pipe is causing, you know, just with our change in length is FL divided by EA. The force in this rod is going to be the weight of the water divided by 2, half the weight of the water in the pipe, you know, times the length of this rod, divided by E, the modulus of elasticity, the property of the material, divided by the area of the rod. But then we also need to say that, hey, the weight of this rod itself is going to change in length. So we're going to take the weight of that rod, divide it by 2, multiply it by and that's going to be the force that we're going to be used. You know, we just went through that integration. If you just take the weight of the rod divided by 2, hey, that's going to be the axial force that's going to stretch it out. So weight of the rod divided by 2 times the length of that rod divided by EAR. And we know everything about this. This is known. This one we don't know WP. So we're going to do the same thing for this rod up here. Now this rod is going to see the entire weight of the pipe. So FL divided by EA is the entire weight of the pipe times the length of this rod divided by E times divided by the area of that rod. And then we say, hey, this rod has weight. That weight of the rod itself is going to lengthen itself out, but it's only going to be half the weight of the rod. Cool, so that is known. And then we know the weight of the rod is just the area of the rod times the length of the rod times the weight density. So that's what those are. And if we, and even here, if we know the weight of the rod is the area of the rod, that area is going to cancel that area down there. All right, so and then we can just add them all together. So so those two are the change in lengths of CD and change in lengths of FE, and then we have the change in length of the spring. Change in length of the spring. Here's our equation for a spring. F is equal to the spring constant times its change in length. We rearrange for change in length, and we have the force of the spring is divided by the spring constant. The force in these springs, because the water weight is a half and half, the weight in the spring is half the water in the pipe. Alright, hell yeah. And then we put this equation all together. So we have the change in length is going to be the change in lengths of the two thin rods, plus the change in lengths of the bigger rod, plus the change in lengths of the spring. Now in this, hey, these are the only three things we. This is the parameter that we want to find. So I'm going to isolate that. I'm going to factor that out, and then those extra three terms are going to be right there. And then I'm going to add the other two terms. And then I just need to get this by itself. So I'm going to take these two terms and subtract them to the other side. And then I just shifted that over here. So that's this minus those two terms. And then I'm going to divide by that. So that's what I did there. And then just threw in all the numbers. And so the total change in length is 82 millimeters. Just always use meters, always use newtons. So this is newtons per meter cubed. This is in meters. This is in this is the modulus of elasticity. This is in newtons per meter squared. And even the spring constant is 60,000 newtons per meter. So there you go. In the area, in the diameters are in meters. And hell yeah, and like I said, it doesn't change at all, but that was just fascinating. That's why, and there's just so many places to make errors if you got into a problem and you're just like, I mean, you could also say the water, you know, let's say this is a hot sunny day and it's 90 degrees out, and now you've got cold mountain water running through it that you didn't. You turned on the water, and then so this whole system like cools off. Well, maybe that reduces, everything's going to contract. Let's say the weight, the temperature of the water is actually the temperature of this entire thing, due to it just being metal or something, and you could take that into consideration, and it's going to be, who cares? That's going to be even more who cares than the actual fact that we do have a change in length, just the fact that these rods have weight. So that's what we went over in this video, and just because going over a whole problem, it's, you know, and then that's why I kind of just did it on my own and then did the integrations, just because it gets a little bit heady, because like finding the change in length due to something hanging under its own weight is a separate problem, and the fact that you have to like one problem can be a combination of a bunch of littler problems, make things difficult, and places where you can just run into a lot of errors. So the first thing I did is just say, hey, let's just say none of these change length at all, and we don't know about material mechanics, but we do know about spring mechanics, and that's what we did at the very beginning. If you just say the 82 millimeters is just due to the weight, you know what I mean? So a spring constant is force, K, change in length. So let's figure out what the force would be. The change in length is going to be 0.082, and this is going to be times 60,000 newtons per meter. Hey, that was pretty easy. 60,000 times 0.082, and I'm just going to say the weight of the water is 4,920. Times 2. Sorry about that. And we have 9,840. So the actual answer is 9,685. So it's actually less. So these springs aren't being deflected because, hey, like the actual deflection of these members is about 1.5 millimeters. And so we have a little bit less deflection. We only have 80 millimeters or 80.5 millimeters of deflection in these springs. And then some of the deflections in those. So if we take that in consideration, it does change it. I can't even wrap my mind around why that would be a lower number compared to just saying the 82 millimeters of deflection is just in the springs. And is it a lower number? Yes. So, but yeah, kind of an interesting problem. But I would start there and then do the lengths of the springs. But it was just fascinating. You wouldn't have to. You could neglect. And as doing problems or an engineering, you know what I mean, thing, you can go back and make something more complicated. But I think it's good just to have an idea of like, hey, what things can we neglect? And we can neglect the lengthening of this rod due to under its own weight. Like that's like small potatoes compared to the weight of the water in the pipe. If the weight of the water in the pipe is about 10,000 newtons and this rod weighs about 1 newton, you know what I mean? And there you go. You know, because I was always saying like, well, how can you sorry about that. How can you determine if something is negligible? Well, see if it's if it's like the first 3 units are what's going to drive this. The fact that it's 10,000. You know what I mean? If I said this was going to be 10,001 newtons, well, that number. So we have 5 digits that are driving this, and that number is in the first digit place. You know what I mean? So the first 3 digits, especially if we're just trying to get a number to 3-digit accuracy, maybe this 4th digit might apply. But in this case, we have a 5th digit, so I can just say that would be negligible. That there is some problems that I've done this year where I had to do that. If you had something that's like 10 to the 10 plus 10 to the 6. Cool. That's negligible, and you know it's harder to see that, but you know what I mean. You have you know this is 4. Well, that's only 4 decimal places away. You know what I mean. So maybe, but if you had 10 to the 10 plus 10 to the 5, that's exactly what this is. This 1 is 1 times 10 to the 0, and then this is 1 times 10 to the 4. Oh yeah, so and that's 5. That's a separation of 5 digits. So there you go. So that would be that example. That's what I thought. So if we have 10 to the 10 plus 10 to the 6, this is negligible, and you just disregard it. All right, hell yeah. So I'm going to be done with this. I'm going to try to post it. Thanks for joining me, and that's a video.